The physical reality of global routing is incredibly dense. Millions of miles of glass fiber pulse with data, connecting massive server arrays across continents. But inside this infrastructure lies a structural routing problem. Devices operating on private IP addresses, such as the 10.network space, are strictly non-routable over the public internet. Look at this topological map. You have a private subnet at Site A and a private subnet at Site B. They are physically separated by a vast cloud of intermediate public internet routers, creating a hard barrier that prevents direct communication. A virtual private network is built to bypass this barrier. Structurally, a VPN is an overlay network. It achieves a logical topology built directly on top of this disjointed physical infrastructure. This logical topology is not built with cables. It is constructed through two highly specific mechanical operations occurring at OSI Layer 3, encapsulation and cryptographic payloads. Solving the VPN problem requires forcing an untrusted public network to carry strictly private data, accomplished by manipulating the standardized architecture of the packets themselves. Let's track a single standard Layer 3 IP packet generated by a host located on the internal private subnet. Here is a block diagram of that packet. It carries a baseline IP header specifying a private source address of 10.0.0.5 and a private destination address of 10.0.0.10, followed by its payload. This packet transmits from the local switch to the edge router, sitting directly on the boundary of the public wide area network. Here, the transmission fails. The public internet's border gateway protocol is strictly configured to drop RFC 1918 private address packets. The packet is dropped entirely. You might ask why the router doesn't simply rewrite the source and destination IP headers, replacing the private addresses with public ones. The receiving internal host at the remote site requires the original, unaltered private IP data to correctly maintain and process the specific internal connection state. Modifying any part of that original header destroys the host-to-host connection before it can even be established. We are left with a strict operational paradox. The packet must physically traverse the public internet completely unaltered, yet it must somehow become publicly routable without changing its private identity. The primary mechanical solution to this paradox is encapsulation. Watch the diagram expand. Instead of modifying the data, the edge router treats the entire unaltered Layer 3 packet as raw payload. It encapsulates the original packet by prepending a brand new IP header to the front. This new outer IP header utilizes valid, globally routable public IP addresses, specifically the public addresses of the two edge gateways. Let's shift our perspective to the intermediate routers operating on the public internet. When this packet hits transit, these BGP nodes only scan the outermost IP header to make their forwarding decisions. The internet infrastructure is entirely blind to the inner packet. It treats the original private data merely as unexamined weight attached to the new header. By wrapping the completely unroutable packet inside a routable vehicle, the private data successfully crosses the public gap. The packet travels node by node until it arrives at the destination edge gateway. Here, the decapsulation sequence executes. The receiving gateway strips away the outer IP header, exposes the original private packet, and pushes it safely into the internal subnet. This encapsulation process alone is what actually establishes the structural tunnel between the sites. However, relying solely on encapsulation exposes a fatal flaw. The payload is traversing public space in pure plain text, readable by anyone monitoring the wire. While encapsulation perfectly solves the routing problem, a pure tunnel is practically useless in modern networking without the imposition of a mathematically rigorous cryptographic state. Sending data over untrusted IP routing carries a strict requirement. We must impose strict authentication, guarantee its data integrity, and ensure complete confidentiality. This state is generated by the IPsec suite, specifically relying on a protocol called Encapsulating Security Payload, or ESP. The first phase of ESP secures the payload. A symmetric cipher, typically AES, is applied directly to the inner packet, converting it to ciphertext. Notice how the new ESP header is inserted squarely between the unencrypted outer IP block and the encrypted inner packet. This cipher ensures complete confidentiality, mathematically locking out intermediate service providers or intercepts from reading the payload. Confidentiality solves the privacy issue, but it triggers the secondary requirement, payload authentication. The receiving gateway must know the data was not tampered with. ESP handles this by generating an integrity check value, created by running a cryptographic hash across the encrypted payload. This calculated value is appended to the absolute tail end of the packet structure as an off tag. The off tag provides a strict mathematical guarantee. If a single bit of the payload is altered in transit, the hash fails, and the receiving gateway will instantly drop the packet. Now, compare this newly secured payload against the outer IP header. You'll notice a strict operational necessity. The outer IP header must remain completely unencrypted and exposed in plain text. If the outer IP were encrypted along with the payload, the public routing infrastructure would have no destination data to read, causing an immediate routing failure at the first hop. True VPN security is not a physical barrier built around a network. It is a mathematically enforced state of confidentiality applied individually to millions of discrete packets. When deploying IPsec, systems engineers face an architectural fork. They must choose between tunnel mode and transport mode. This chart compares the two structures. The top row illustrates tunnel mode. It relies on the dual IP header design we just built, keeping the entire original packet intact beneath a new outer IP. Tunnel mode is strictly deployed for site-to-site connections. Gateways handle all the encapsulation math automatically, leaving internal hosts completely unaware of the process. Transport mode, on the bottom row, is engineered for direct host-to-host connections. The key structural difference in transport mode is immediate. No new outer IP header is ever generated. Instead, transport mode encrypts only the payload of the existing IP packet, preserving the original IP header for routing. Choosing between these modes dictates hardware requirements. It determines whether massive network gateway appliances bear the heavy processing overhead, or if individual user endpoints must compute the cryptographic algorithms themselves. Let's shift our perspective away from the microscopic packet architecture, back to the macro-physical infrastructure of the Internet. Watch a single packet's journey. The packet hits the network edge, triggering the mathematical processes of encapsulation and AES encryption. It enters public transit, moving across intermediate BGP routers that view it merely as a standard, independent datagram, scanning the outer header and passing it along. Despite the terminology, there is no physical continuous pipe bridging these two sites. There is no dedicated connection state. What actually exists is an abstract sequence of nested geometric layers, mathematical headers locking together at high velocity. The illusion of a secure tunnel is generated solely by the gateways, mathematically assembling and disassembling these packets thousands of times per second. Virtual private networks represent the ultimate abstraction in systems engineering. They entirely decouple logical network design from the hard realities of physical infrastructure, achieved entirely through the rigorous application of mathematics.